Well, there are 10 of us here now, and it is 2 minutes past 7. I can see, let's see, 1, 2, 3, 4, 5 of you have checked in. There's 5 more people watching that haven't checked in. But hopefully you can all hear just fine and see just fine. That's the goal. And if you have any questions, you'll let me know in the chat. Let's see. I did do a final review session already for the seniors, which is already posted on this same YouTube channel and linked in Google Classroom. So you can use that already. In that review session, I started at the beginning of the review questions and worked forwards. And then at the end, I went and did a couple that people asked about. I am thinking that in this review session, I will do the opposite. I will start at the end and work backwards, and we'll see what kind of overlap we have. If there's any questions that you have in particular, or that you want me to cover in more depth, please let me know, either now or if we get to them later on. I may want to make sure that I answer any particular questions. The best case scenario would be that you've already watched the senior review session and you have already found the questions or the things I didn't explain very well and already know exactly what it is you want. So if you have any of those questions already, that would be wonderful. But if not, I will go to the end and start from there and work backwards. Also, to let you know, I did change the numbering for next year as I was looking at that document, and the numbers I have up here on the screen are different numbers than you have, but they're the same questions in the same order. So I apologize if that numbering is confusing. Again, just to be clear, I'm starting at the end and working backwards. The numbers in my document are not the same as the numbers in your document. Apologies. Hi, Tracy. Okay. From the very end, which in my document is 21, but I know is not 21 in your document. Again, hopefully the numbering issue is not going to confuse anyone. Tracy, my day was pretty good. I hope yours was also. Thank you. Here in this question, it says, at right is a function g formed by 2 parabolas. You are to first write a piecewise definition for the function, then sketch the new function, which is a translation of g of x given by g of x minus 3, and define it. Then you are to sketch k of x given by g of x over 2 and define it. And then describe how the transformations impacted the domain restrictions. Okay, let's start at the beginning. A, write a piecewise definition for this function. Okay, so I have here a couple different parts. I'm going to say the first part will be in blue. The second part can be in green. And the third part can keep its original red color. And let's see, I have g of x is equal to, this is part A, equal to the 3 pieces. First of all, the blue piece is a parabola. It has a vertex at -2, 4, and it opens down. So I'm going to say this is just an x squared function, a parabola, that's been translated left 2 and up 4, and I made it negative because it opens down. And this is the function if x is less than 0. Okay, and then I have this middle part, which is green. The green is just the dot, 0, 4. So 4, if x equals 0. And then the last part is in red, and that's also a parabola, but it has a vertex at 2, -4, and it opens up. So I will make a positive parabola that has been translated to the right 2 and down 4 if x is greater than 0. There we go. That's A. That is a piecewise definition for that function. Cool. And now it says, I need a new color. I'm going to go with purple. Sketch h of x equal to g of x minus 3. So that means that this whole function has been translated to the right 3. So I'm going to move all the points right 3. 1, 2, 3. There's that point. 1, 2, 3. You forgot the squared. I forgot the squared. Oh my God. Thank you, Shaheen. Thank you, Tomas. Squared. What am I doing? Good catches. Whew. Sweet. Okay, I was back. I was doing part B, and I'm translating right 3. 1, 2, 3. There's that. So it goes like that. 1, 2, 3. It's going to come down to this spot here. And then it's going to have a hole. And then it's going to have that point 3 to the right. And then it's going to have this point 1, 2, 3. And be down there. And then go up like that. Great. For the blue one too. Oh my gosh. Thank you, Tomas. What am I doing? Squared functions. X squared. Much appreciated. Okay. Whew. Part B. This is h of x. And it equals the 3 pieces again. And in this case, I'm going to show first an expanded notation because I want to watch this x minus 3 get plugged in. So I'm going to show that it's this part, the blue part, and instead of x, I'm going to write x minus 3, and there's the plus 2, and there's the squared, and there's the plus 4. If, and I saw an x, so I'm going to write x plus 3 less than 0. And then 4, if x plus 3 equals 0. And then here's the last part. And instead of x, I'm going to write x plus, x minus 3. Oh my gosh. Lots of mistakes already. I must be tired. X minus 3. X minus 3. X minus 3. And this time it's minus 2 squared and minus 4 if, and I'm going to put in here x minus 3 is greater than 0. Okay, now obviously this is a pretty ugly way to write it, but I really wanted to be explicit that all we did when we do g of x minus 3 is replace all of the x's with x minus 3's. And when that happens, obviously the better way to write this would be h of x equals negative 3 plus 2 is minus 1, x minus 1 squared plus 4 if x is less than 3, and 4 if x equals 3, and x minus 5 squared minus 4 if x is all that happened with x minus 3's. And the impact on the graph then is to translate right 3. So this point, which was here, moved, which was left 2, -2, moved to +1, +1. This point, which was here, or here, which was right 2, moved to right 5, right 2 here, moved to right 5 here because of this 3. And this moved to here, this moved to here, this moved to here. And I think this in particular is really effective for thinking about what happens when we do g of x minus 3. Look at these x values. These are when we plug in x minus 3 in this domain restriction, x minus 3 less than 0 is the same as x less than 3. When I isolate x, I have to add 3 to both sides, and I get x less than 3. We can really see visually why the x minus 3 input moves right 3 in a positive direction when we do this. Anyway, that's enough about part B. Part C was next, and again, I want a new color. I'm going to do part C in this lovely yellow. And we're going to have g of x over 2, which is going to dilate the original function out by 2. Spread everything twice as far from the y-axis. So we're going to have this point, which is at 4, go to 5, 6, 7, 8. And this point, which is at 2, go to 1, 2, 3, 4. And this point, which is at -2. Do you need to write the functions 2 on the test for B and C? So sketch h of x, Tomas, was what I did here. Define h explicitly in terms of x is what I did here. Hopefully that answers your question. So the instructions were quite explicit. You had to make a sketch, and you had to write the definition. Shall I label it? Define explicitly. Did I answer your question, Tomas? Hopefully. This circle stays here. This point stays here. This -2 goes twice as far away. Good. And this 4, 5, 6, 7, 8 twice as far away. So we have this new function, which in yellow goes up, and that's ugly, goes up and down, off like that, and then down and up like that. Cool. So here we have, now this is k of x, and I'm on part C. K of x, give myself a little more space. K of x equal to the set of functions, and the first one, and again, I'm going to show really explicitly that substitution for x with x minus x over 2, right? That's what we get here, and it was plus 2 squared plus 4 if, and again, let's show it, x over 2 is less than 0, and then here it's 4 if x over 2 is less than 0, and then down here it is x over 2 minus 4 squared minus, oh, shouldn't be minus 4, minus 2, my fault, x over 2 minus 2 squared minus 4 if x over 2, and that's got to be an equal 0 here. And this is greater than 0. Okay, obviously x over 2 equals 0 is just the same thing as x equals 0. But I think it's worth noting the substitution. Well, all we do when we find k of, or g of x over 2 is plug in x over 2 for x. Okay, that was part C. D, describe how the transformations that occurred to map g to h and k change the domain restrictions of g of x. Cool, so last piece here, we're saying part D, and we're going to write h of x map, or translated g of x to the right 3. All of the domain restrictions in g of x also moved right 3, because maybe that's not a period. Substituting x minus 3 for x in x less than 0 yields x minus 3 less than 0, which is equivalent to x less than 3. The dilation in k of x did not change the domain restrictions in g of x. Right? We can see that pretty clearly. Here, these zeros moved right 3 and became 3s, but here these zeros stayed zeros. This was right 3, no change. Any questions on this last problem on the review sheet? Oh, and welcome Vanessa and Maritza. Glad you're here. Hello. Explain the dilation again. Yeah, of course. Sure. Let's visualize that a little better, and I'll clean off this graph a little bit. Great question, Shaheen. Okay, so here was the graph of g of x. This is g of x. And yeah, the graph part, I'm on it, agreed. And we're supposed to graph, and I'm going to do it in yellow again, k of x, which is equal to g equals g of x over 2. Okay, so what that means is that for any x value, it would need to be twice as large to give the same output in g of x as it did in k of x. So I know here in g of x that -2 yields 4. Well, some x value is going to be plugged into g, get divided by 2, then input into g, and then it would be a point on k. So if -2 yields 4 in the g of x function, I'm going to say to myself, well, I know that g of -2 equals 4. That's a thing I know. So if I also know then that by definition, k of x equals g of x over 2, then I can say, all right, I want to get the input -2 into g because I know what happens. It's going to make 4. So I'm going to say k of -4 will equal g of -4 over 2, which is g of -2, which equals, because we just wrote it down, this equals 4. 4. So that means that if I plug into k, -4, I will get 4. K of -4 equals 4. Well, let's graph that. -1, 2, 3, 4, up 1, 2, 3, 4. So what happened was this point, -2, 4, got stretched away from the y-axis by a factor of 2. That's what's happening here. Dilate about y-axis by a factor of 2. So this point stretched away from the center, the y-axis, by a factor of 2. See, it was 2 spaces away, and now it got stretched out another 2 spaces away to that spot. Same thing happened here. This point was -4, 0. Again, I can walk myself through the same process. Right? I can prove it to myself functionally, even if I don't know it from a transformational perspective. I know that this is g of x over 2. I'm going to say, all right, a thing I know about g of x from this red graph is that g of -4 will equal 0. By definition, I know that k of x equals g of x over 2. Well, what x value could I plug into this expression, x over 2, and get -4? Because I know what g of -4 is. Obviously, -8. So I'm going to say k of -8 will equal g of -8 over 2. -8 over 2 is -4. So this is g of -4. What is g of -4? Well, quite clearly, 0. 0. K of -8 equals 0. Okay, so I can graph that. 1, 2, 3, 4, 5, 6, 7, 8. 5, 6, 7. Right there. And again, I can see that this point was 1, 2, 3, 4 units away. And it got stretched out by a factor of 2 so that it got double the distance away from the y-axis. Right, here is those 4 units, and that distance got doubled. 2 units got doubled. Oh, and I was trying to make that in yellow. So there was, oh, ugly, the new graph. And that same process happened for every little point on here, right? Here was 1 unit away, and that got doubled, an extra unit away, right? And here was, this was 1, 2, 3 units away, and now it's 1, 2, 3, 4, 5, 6 units away. This point should really be clearly right here, 6 units away. Cool. Then lastly, Shaheen understands it now, but he asked the question, so he has to watch me do it. Let's think about it once more visually, because I think the visualization of these transformations is like a really good framework. So visually speaking, we can see, let's look just at that left side part. It was x, it was negative x minus 2 squared, oh, sorry, x plus 2 squared plus 4. So that was just the red part, right? And let's put it on just its domain, which was x less than 0. There it is. And let's call it g of x. And we can now see visually what happens as we plug in g of x over some slider a, which we are going to let vary from 1 into 2. And watch as that red graph gets stretched out, stretched out, dilated till it's twice as far from the y-axis. Right? We can see that happening really powerfully. Let's turn this on brighter so you can see it even better. Right? There it was. This is the original graph. And as I dilate by a factor that approaches 2, the graph gets stretched away from the y-axis. Dilated away from the y-axis by a factor of 2. Cool. I did that same thing to all the other points. I graphed down there, and I graphed out here, and I sketched whoop, like that. That was an excellent question. I'm glad we thought some more about that. Any other questions about this last problem from the review sheet? What's yikes? Yikes isn't a question. No yikeses. Okay, Maritza, I want to be as kind to you as possible, but I don't think you really understand what it means to ask a question about the math. I want you to go ask questions about the math and understand the math. The goal of the review session is not so that you know exactly what's on the final and I tell you all the answers. The goal of the review session is to understand the math carefully and precisely. But the final exam is 10 questions long, one optional question on sequences and series. I can't remember how long it was last semester. Was it about 10 questions long last semester? You tell me. Tomas, excellent question. That's a math question. And you're asking me, why is it that the domain for k of x did not change? Well, I guess the domain of all three functions didn't change, right? The domain of all three functions was just all real numbers. So it didn't change in any case. But I think, Tomas, that you're really asking me, why did the domain restriction not change? And the answer to that is because here, when I plugged in x minus 3, I go right 3. I was starting at 0, and right 3 changes 0 into 3. But here, when I times by 2, 0 doesn't change at all. You times 0 by 2 and nothing happens, right? If I wrote this again, I could say this is negative. This is, again, a rearticulation of k of x, and it's negative x over 2 plus 2 squared plus 4. What happens when I times by 2 on both sides? Nothing happens to the 0, right? X is less than 0. 4, again, same thing. Times by 2 on both sides, still just x equals 0. Here, x over 2 minus 2 squared minus 4 if x is greater than 0. So that these in the original, which I erased, sorry, were the same as these here. Visually, we can see that when I move that red graph right 3, I think I did that in purple, right? Let's do it again in purple. Then all of these domain restriction issues here in the middle at 0 changed. They moved to 3. But when I, from 0 times by 2, nothing happens because you take 0 and times by 2 and nothing happens, right? Here, this 0 spot is going to move 1, 2, 3 spaces. But when I times by 2 on this yellow graph, 0 times 2, nothing happens. 0 times 2, nothing happens. It doesn't mean that timing by 2 would never change domain restrictions, right? I could make a totally new graph. So Tomas is prompted. This is not even on the review sheet. I'm just making up extra math to illustrate a point. If I had a totally separate graph that arbitrarily looked like this is at 3, and it goes up and down like that. Maybe this looks kind of familiar. And I said, this function is g of x. And I said, now, graph g of x over 2. This would change, right? Now, in green, this would go, here's 6, right? And this would come out and go that way. And this would come out and go that way, right? Oh, that was terribly bad, but I think hopefully you get the idea. Here, the domain restrictions did change when I did this transformation that dilates about the y-axis by 2. Here, this 3 turned into 6. It's only the specific thing of 0 being times by 2 where no change happened. Did I answer your question, Tomas? The reason this didn't change is because the domain restrictions on the original function g were at 0, right? 0, 0, 0, 0. You times 0 by 2 and nothing happens. Whereas if you add 3 to 0, it changes. Yeah, because the domain restrictions were at 0, nothing happened. If the domain restrictions had not been at 0 and we times by 2, something would have happened. I think you're on it, Tomas. Any other questions? Those were both great questions. Any other questions on this last question on the review sheet? Vanessa, if I could answer the question, yikes, I would, but I don't exactly know how to respond to it. Okay. Again, like I said, I'm starting at the very end and moving backwards. So here was the second to last question. Vu goes out for a run. He runs away from home at a pace of 6 minutes per mile. After running for 4 miles, he stops for 6 minutes for a drink of water. Then he jogs home. In total, he was gone for an hour. Sketch a graph of his distance away from home over time. Include a scale and labels on the graph and write a piecewise definition for the function. Okay, let's do this in black. Again, I know that the numbering on my version here is not the same on your numbering. Hopefully no one's confused. This is just the second to last question. Here it says 20. I think that it is not number 20 on your version. Okay, so Vu started at home. He runs away from home at a pace of 6 minutes per mile. So he started at home. Home. This graph is sketching distance from home. Distance from home. Yeah, thank you, Cindy. I did slip up there. Home, distance from home, and time. And this is going to be in miles. Miles. And this is going to be in minutes. Okay, and let's see. He runs away from home at a pace of 6 minutes per mile, and after running for 4 miles. So here we go. This is 4 miles. If he's running 6 minutes every mile, I'm thinking that 4 miles should take him 24 minutes. 24. 24 minutes, 4 miles. Whoop. Good running, Vu. Then he stops for 6 minutes. So 24 plus 6 is 30. He didn't get further away from home. He didn't get closer from home. And yes, Vu did zoom away from home. Sorry, Vu. And then lastly, he jogs home. He's relaxed. The 4 mile jog home takes him another 30 minutes. Okay, because he was gone in total for an hour, 60 minutes. Here is Vu zooming not quite so fast towards home. Great. Sketch a graph of his distance away from home over time. Check. Include a scale. Check. And labels. Check. On the graph. Write a piecewise definition for the function. So I'm going to call this function distance away from home at time t. And it has 3 parts. Let's color code them. There's the purple part and the green part and the blue part. And we're going to start with the purple part. And let's see. The slope here is up rise of 4 miles in 24 minutes. So that was up 1 mile in 6 minutes, or rise of 1 over run of 6. So 1/6 x. If 0 is less than or equal to, oh, and I said this was t. Just kidding. T. T for time. 1/6 t. If 0 is less than or equal to t, less than or equal to 24 minutes. Then he stops for a drink of water, and he is now 4 miles away from home. 4. If 24 is less than or equal to, oh no, I shouldn't say less than or equal to, because I've already defined what happens at 24 here. So here I'm going to say 24 less than t less than or equal to 30. And then last part I did in blue. He's now going down towards home. So I'm going to make it negative. He goes down this 4 miles in the course of 30 minutes. Rise of 4, run of 30. I could write 4/30ths, or I could write the simplification 2/15ths, or 1/7.5. Anyway, I'm going to write 2/15ths times t minus 60, because I can see that this graph meets the origin at 60. If 30 is less than or equal to t less than or equal to 60. Done. Excellent question, Tomas. It does not matter if you define 24 in the first function or the second. You could have put it in either spot. You should definitely define what's happening in 24, and you should not define what's happening at 24 in 2 different intervals. That would be bad, but it would be just as good to say that t is defined here in green and not here in purple. That would be equally as acceptable, as long. Great question. Other questions about this problem, the second to last. Cool. Thanks. What's up, Fish? How's he doing? And let's see. Oh, sorry. I said hi to Cynthia's brother, Marco. Maritza, great question. I was so excited that no one asked that because I figured you all understood it. Maritza, can I say appreciations that you're asking a specific math question and not just what's on the final? That's great. How did I get this negative 2/15 t minus 60? So I saw on this blue part that the graph went down 4 miles. He went 4 miles closer to home and over 30. So being somewhat familiar with Algebra 1, I knew that the slope of a line would be given by its rise over run. So I said that the slope m for this blue section would be equal to negative 4/30ths, which I reduced to negative 2/15ths. Now, if I just graph the line like here, this was just 1/6 t, right? Up 1 over 6 t, right? If I just graph the line of negative 2/15 t, if I said it was y equals negative 2/15 x, y equals negative 2/15 x would be not the line I wanted. It would instead be this line here. There's y equals negative 2/15 x. Well, I don't want to graph that line there. If I graph this line here, then by the time I get to 30 to 60, it'll be way down there. I don't want a line way down there, because it would say that after 30 minutes, Vu had suddenly teleported to a negative distance away from his home. And I'm assuming that Vu can neither teleport nor land at negative distances away from home. Neither of those being possible in the modern sense of time and space. So what I did, instead of telling Vu that he should teleport to a negative distance away from home, was say, let's put the function in the right place. And I could have, in order to put the function in the correct place, translated it up, but I didn't really know what the y-intercept was. What I could see really clearly was that the x-intercept was at 60. So I said, what should we do? Well, let's take this blue line and move it over here, right 60 spaces. So I used this translation, right 60. And I said, okay, let's put Vu in the right spot. Like that. So this was the slope. And this was translate right 60. Okay. There is an extended debate in the comment section, the chat section, about whether or not Vu can or cannot teleport. There is mass evidence that he does have the ability to teleport. Maybe this other Vu in the math problem can't teleport. Regardless, I did want him to have a continuous function where he did run home, because the instructions said that he just jogged home and didn't teleport to a negative distance away. But more importantly, Maritza, I hope that I answered your question about how I found out that this part should be negative 2/15 t minus 60. Got the slope from right here, and then I brought it to the right spot by going right 60. And it appears that Cynthia's brother Marco possibly has taught Vu the magic of negative distances away from home and also teleportation. But Maritza, did I answer your question? Should we look at it again? We could pull up Desmos and look at it that way. That'd be another framework for thinking about what this was. So we knew the slope was negative 2/15 x, and it looked like that. And we said, okay, what we want is for it to be, let's see, here are all the pieces that I wanted to get. Let's graph it out. And if I say, let's see, capital D of t, and it's going to equal the piecewise function, which is defined first 0 less than or equal to t less than 24. And on that domain interval, it will be 1/6 t, 1/6 t, 1/6 t, and then comma, and then on the next domain interval, it's 24 less than or equal to t less than or equal to 30. And in that section, we've got just 4. There we go. So we're seeing, here's Vu stopping for a drink of water. And And last section, he's going to run home. And the domain restriction we know is 30 less than t less than or equal to 60. And then let's watch what happens if I just write in here negative 2/15, because I know the slope, times t. Look at how bad that looks. Goodbye, Marco. Take it easy. Look at it. We can see so clearly the way that this negative 2/15 t just did not work. Now I could translate it up to get it to match, right? I want it to match. I want this section here needs to fit with this whole rest of the graph, right? This other VU in the problem did not teleport, even though the real VU could have. So I want no teleportation to happen. I want a continuous motion for VU. So I know that this last section is in the wrong spot. Again, I could have just moved it up, but I would have had to figure out the math to figure out how to move it up. So what I can do a lot easier is just move the function to the right by saying, I don't want negative 2/15 t, I want negative 2/15 t minus 60. And then it matches so very well because it stops here at 60. Sweet. That's what the graph should have looked like. Okay? And Maritza understood that long ago, and then I just kept talking and talking and talking, but she puts up with me anyway. Excellent. If there are no further questions on VU's exciting trip away from home, I will move back to this other piecewise graphing problem. Okay, it says sketch a graph of the function f of x equal to, on the domain, negative 2 pi less than or equal to x less than negative pi sine of x. Then on negative pi less than or equal to x less than pi, we've got negative cosine of x over 2. And then lastly, pi less than or equal to x less than or equal to 2 pi. The function is negative sine of x. So let's see. I'm going to use the strategy we practiced in class, which was to make a table for piecewise functions and include some values in each domain interval. So I'm going to say, let's color code and say this part will be in blue, and this part will be in green, and this part will be in purple. And I'm going to make a table that says here's x, and here's f of x, and here's the output, y. And I want some values between negative 2 pi and negative pi. So I'm going to certainly include negative 2 pi. And then I'm going to include, let's see, how about negative 3 pi over 2? Because that's less than negative pi, but greater than negative 2 pi. And then, let's see, I think I want to switch into the green section and put negative pi here. And actually, just for reference's sake, I'm going to do negative pi twice. I'm going to do negative pi in blue, even though I know that negative pi is not defined in blue. I'm going to put it in quotation marks. But just because I want to reference it, I'm going to also show negative pi in green, because I want to think about what's happening at that negative pi. I really want to know, in order to graph, does the blue one match up with the green one? So I'm going to kind of check in blue what happens at negative pi. Okay, and then I also want to know, how about 0? And then again, I'm going to put in quotation marks here, pi in green, even though I know clearly that pi is not defined in the green section. Pi would be defined in the purple section. So here in the purple section, pi again. But again, I want to know what's happening at pi. Would the green part match up with the purple part? And then let's see some values between pi and 2 pi. So 3 pi over 2, and then 2 pi. Cool. So let's see. Negative 2 pi, what is the sign of negative 2 pi? And I'm sure you're all at home shouting out in your heads that obviously the sign of negative 2 pi is, so I'm writing here, sign of negative 2 pi, which of course is 0. and then the sine of negative 3 pi over 2, which of course is sine of negative 3 pi over 2, which of course is 1. And then the sine of negative pi, which again, I'm going to put in kind of quotations here because we know it's not really on the graph, not part of the blue interval, but just for reference sake, the sine of negative pi, if it were on the graph, is 0. Again, quotation marks, right? Not a value in f of x. Okay, and then let's see. If I actually plug negative pi into the function, what would happen is that it would get plugged into negative cosine of, and here's the x, so negative pi over 2. Now, the cosine of negative pi over 2, just like the cosine of pi over 2, is 0, and negative 0 is 0. So look at this. If I had plugged negative pi into the blue function, I would have got 0. And when I actually plug negative pi into the green part, I still get 0. So negative pi 0 is a point on the graph. Even though this negative pi 0 didn't exist, negative pi 0 still is going to exist on f of x. Okay. Then let's see. Negative cosine of 0 over 2. The cosine of 0 is 1, so negative 1. And then negative cosine of pi over 2. And again, I'm putting this in quotation marks because I know it's not really on the graph because clearly pi is not defined in the green section. It would be defined in the purple section. So let's see. Cosine of pi over 2 is 0, so negative 0 is 0. And then in purple, where pi actually gets plugged in, we're going to have negative sine of pi. And the sine of pi is 0, and negative 0 is 0. So again, we have the same situation, right? Where this green one, which is not, again, not the value in f of x, because if I actually plug pi in, it would actually go here. But the spot that it would have been here if it did go here is the same as this one. So the green function is going to end at the same spot that the blue function would pick up. My overall point here is that this whole function is continuous. And then 3 pi over 2, and just to reiterate that, if these were not the same, the function would be discontinuous. But because these are the same and these are the same, the function is continuous. Okay, negative sine of 3 pi over 2. Let's see, 3 pi over 2, the sine is 1. Oh no, the sine is negative 1, so negative 1 is 1. And then 2 pi, and negative sine of 2 pi. The sine of 2 pi is 0. Negative 0 is 0. Okay. That was fun. Now let's sketch a graph. 2. And here's 2 pi. And here's pi. And here's the same amount. Pi. And 2 pi, and up to 1, and down to negative 1, and there's negative 3 pi over 2, and there's 3 pi over 2. And first the blue section, which starts here and goes up to 1 and down to 0. Oh, but it doesn't actually go down to 0, right? I could fill in a little open circle in blue if I felt like it. And it would go up and then down. And then green fills that in, right? Green is going to fill in that circle because green actually exists there. and it goes down and then up. And then there would be an open circle here in green, but the purple part fills that in and goes up to 1 and down to 2 pi. Beautiful. Any questions on that third to last problem? Again, it says number 19 on my paper, and I realize that it doesn't say number 19 on your paper. Cool. Seems like absolute and complete understanding. That's my favorite. Okay. This is the problem where I had multiple students who said it was so easy that it seemed like a trick question, because how could a problem ever be that easy? But literally the way you derive the double angle formula for tangent is to take the angle sum formula and plug in the sum of two of the angles. So the angle sum formula for the tangent ratio, you could grab on your identity sheets. You might write down on your note card, if you were making a page of notes right now, is that the tangent of some angle theta plus some angle phi is equal to the tangent of theta plus the tangent of phi all over 1 minus tangent theta tangent phi. Okay. And then if you want to get the double angle formula, well, the double angle formula is for tangent 2 theta, which would just be the same as tangent theta plus tan theta. So we can apply then our angle sum formula and plug in theta and theta. So I'm going to get tangent theta plus tangent theta, because I'm plugging in theta in place of phi, over 1 minus tangent theta tangent theta. And when I do that, I will find that to simplify, tangent theta plus tangent theta makes 2 tangent theta. And on the bottom, 1 minus tangent theta times tangent theta is tan squared theta, which is, of course, the double angle formula for theta. This here is the answer we wanted to arrive at. The way you get to it is by taking 2 theta, splitting it up into theta plus theta, and applying the angle sum formula for the tangent ratio, which was here, theta and theta, theta and theta, and simplifying to this. And that was it. I think my point here is that there are a lot of identities on the list, but some of them are really easy, right? We made multiple identities because it can be nice to have exactly a double angle identity in some cases, or trying to apply double angles. But it's really just another variation on the angle sum identity, right? There's a whole lot of things on the list, but some of them are just the same things written in a different format. What we're doing with identities is rearranging things to get equal, identical values. So what you see on the paper, even though it looks like a lot, There's a lot of things that are just rearrangements of the same things we already know elsewhere on the paper. I think that's the overall point on asking this question. Yeah, it is an easy question. I want you to notice that things like the double angle formula are not really an extra thing you need to memorize. They're just a rearrangement of the things you might have already memorized, that you might have already derived. Any questions on 18? Okay. Oh, sorry, it's not 18 on your paper. The numbering again is messed up. Any questions on this one about the double angle formula for tangent? Cool. A trig identity. Let us establish it. Okay. I see two fractions, and I see that they have uncommon denominators. Clearly, I say to myself, they need common denominators. Tomas, you don't have a trig identities sheet? And not only do you not have a trig identity sheet, you also don't have the internet to look up the angle sum formula for sine and cosine? It seems odd to me that you're able to chat with me on the internet, but not look up a trig identity. Yes, thank you, Vu. It is on the sheet. But just because I'm a very kind human being who would never mock someone for not being able to look something up, I will write down the angle sum formula for sine, which is sine of theta plus phi. This one we did derive in class, is equal to sine theta cosine phi plus cosine theta sine phi. And remember, this is the one where we did a limited hotspot. It's the kind of hotspot where you can stream video but not do Google searches. I hate that kind. Anyway, this one we did a geometric identity. Right, we rearranged the areas of the trig identity to show that identity, to prove this identity. And then we thought about the way that this is the same thing as rearranging actual algebraic quantities. Anyway, that was the sine, and then you also asked Tomas about cosine, which is cosine of theta plus phi is equal to cosine theta cosine phi minus sine theta sine phi. And you'll, of course, remember this is the same thing as what we did on the paper, except we use alpha and beta. Greek letters are all common ways to name angles in trigonometry. This is clearly the same thing. Alpha and beta as using theta and phi, all the same deal. I think when we did it in class, we did use alpha and beta, but that's no different than using theta and phi. Cosine alpha sine beta. Same. Okay. Cool. Okay, so back to this one, where we were looking at the two separate fractions and we were saying, oh my gosh, these two separate fractions do not have the same denominator. Obviously, our first step will be to give them the same denominator, because what do fractions need except similar denominators? Okay, so if I want to get this denominator over here, I'm going to have to multiply by cosine x over cosine x, which is just 1, so it will not change the value. And here I'm going to have to multiply by 1 plus sine of x over 1 plus sine of x, which again is just 1, and so it doesn't change the value of anything. And when I do that, I, of course, get cosine squared x, because cosine times cosine makes cosine squared, over cosine x times 1 plus sine x. Right, and I'm going to leave these separate and really clearly visually bracketed. And then I'm adding that to 1 plus sine times 1 plus sine makes, let's do the math here. Let's write it out first. 1 plus sine of x times 1 plus sine of x. I'm first going to just write it out so you can all see it very clearly. Over, and the bottom I'm going to bracket it and leave it separate. Cosine of x. And now I have a 1 plus sine of x. And this is still equal to 2 secant x. And now, let's see, I've still got cosine squared x, and this is now going to get added, so I've got one big fraction, and on the bottom, I still have cosine x times 1 plus sine x, and it's still going to equal to secant x. But the work I have to do now is 1 plus sine x times 1 plus sine x. So I'm going to show 1 times 1, which makes 1. And then 1 times sine x, which makes sine x. And then sine x times 1, which makes sine x. And then sine x times sine x, which makes sine squared x. Okay, I now see that I have, a cosine squared and a sine squared. And of course, I think to myself, cosine squared plus sine squared, well, that's just the Pythagorean identity. I know that x squared plus y squared will always equal 1 on the unit circle because I know that a squared plus b squared equals c squared. So I'm going to say cosine squared plus sine squared must make just 1. So now I have 1 plus sine x plus sine x, which is cosine x. 1 plus sine x. This is still the denominator. Nothing's changed. And here is 2 secant x over here. But 1 plus sine is going to make 2 plus 2 sine of x. Same denominator. Cosine x. 1 plus sine x. And it still equals 2 secant x. And then I'm noticing that these look very similar. So I'm going to factor a 2 out and say that would be 2 times 1 plus sine x over cosine x 1 plus sine x. And hurrah, I can feel myself getting close to the end now. What's going to happen here? Well, clearly they will cancel, and I will have 2 over cosine x. And what is cosine x if not the reciprocal of secant x? So if I have 2 over cosine x, clearly I have 2 secant x equal to 2 secant x, and Q, E, D, this is an identity. For all values x, 2 secant x will always equal 2 secant x. Thus, for all values x, cosine x over 1 plus sine x plus 1 plus sine x over cosine x will be identical to the value of 2 secant x. Now, obviously, this is a pretty long way to do it. I showed in excruciating detail all of the distributions and factorizations. I wouldn't think that you would need to show each and every step this way. I would think that probably you could have distributed here pretty quickly, canceled to 2, and gone to here. Anyway, that's everything you need to do to establish that identity. any questions on establishing identities? How did you get from 2 over cosine x to secant x? Excellent question, Maritza. Okay, let's show another step. 2 over cosine x. So let's back up here and not jump to 2 secant x. Okay, there we go. So I'm at 2 over cosine x, and I think to myself, oh, cosine x is the reciprocal of sine x. So I will say cosine x, and I will rewrite it as the reciprocal of secant x, like that. And I'm still trying to prove that it equals 2 secant x. And then I say, okay, knowing that cosine was the reciprocal of secant, I wrote cosine as 1 over secant. And how do I divide fractions? Well, I multiply by the reciprocal. So I've got 2 divided by 1 over secant x. And if I know that in order to divide fractions, I will multiply by the reciprocal, then this will be 2 times secant x, which does equal 2 times secant x. Cindy also had the answer. YouTube has this thing where it flags messages that it thinks are maybe profane or inappropriate, and I have to review them before it gets posted. And YouTube was pretty sure that Cindy was trying to curse with that whole 2 over cosine x nonsense. So I had to approve her commenting on the correct answer before I could show it. But that is the right idea. Exactly. Sweet. Great questions. There we go. That's the whole piece. Yes, yes. Math is rather profane. That's what YouTube thinks, at least. And let's see. Working backwards again. Again, apologies for the change in numbering. I know that this is not 16 on your end, but I fixed the numbering because I didn't like the way it was on your paper. So this is the numbering I want for next year. Explain why establishing an identity means you can only work on one side of the equality. So we should say something like operations on both sides of an equality rest, or let's say, how about this, are only valid if the equality is true. Since to establish an identity entity means to show that an equality is true. You should not assume it's true. In general, contrary to what many politicians seem to think, it is not reasonable to assume your argument is true in order to prove it's true. Clearly, that is a somewhat long and verbose answer that is rather extensive and articulates the same idea in multiple ways. You would not have to write something that long. You probably could have said pretty clearly that you shouldn't assume it's true before you prove it's true. That's the idea. Any questions on this prompt asking you to articulate the nature of establishing an identity? Cool. We got about 6 or 7 minutes before I said I would be done. Is there anything I really need to cover before I go? Anything in particular you wanted me to talk about? Any questions you had that you want to make sure I answer? Pretty sure I covered that for the seniors. I think I covered that for the seniors. Definitely covered that for the seniors. Yeah. So I think everything else you could find on the senior video. But if you had any questions that were specific, you could ask me now. Number 18 on your problem. Okay, so I should find the one where I get yours. Is that this one here? Shaheen? I definitely remember covering 18 on the senior video, but I'm happy to do it again here since I have a few minutes. And Katie says, yes, it was on the seniors video. Yeah, okay, there's mass agreement. Okay. So Shaheen says he's good. Cool. Well, maybe I'll do one more anyway since I have the time. Let's talk about this one. This one's real straightforward. Inverse sine of cosine of 11 pi over 6. Well, let's see. I want to say, first of all, what is the cosine of 11 pi over 6? And in order to do that, I should probably sketch 11 pi over 6, which is over here. And I'll draw in that little triangle. And I'll say that it's a 30, 60, 90 triangle. So it goes over root 3 over 2 and down 1/2. So clearly the point here is root 3 over 2, comma, negative 1/2. And I know that this one is the cosine of the angle, and this one is the sine of the angle. So the cosine of 11 pi over 6 looks like root 3 over 2. So this has become the inverse sine of root 3 over 2. So now my new question becomes, how do I find the inverse sine of root 3 over 2? Well, that's a way of asking, for what angle will the sine be root 3 over 2? Well, that means I'm going to go up here and have to find root 3 over 2 on the y-axis. Here's where the y-axis is at root 3 over 2, right? This is up root 3 over 2 and over 1/2. And now I'm asking, what's this angle that would take me to that value? And of course, this angle is pi over 3. So the answer is pi over 3. Cool. I think with that, I'm pretty sure I've covered in the 2 videos everything on that review sheet, which pretty much covers everything you're going to see on the final exam, except for those of you that have been working on sequences and series, a question on sequences and series and sums, which is kind of based off of the sequence race problems. I will see some of you tomorrow and some of you on Friday. Good luck. It's been a great year. I hope you've learned some trigonometry and or some pre-calculus. And if there are no last questions that are dire, in need of immediate attention, I will bid you all good night and go to bed. Hopefully you're not up too late studying. Vu says half angles. Are any half angles going to be on there? No half angles. We didn't do any half angles. We didn't work with it. I mean, you could make sense of them. They make pretty good sense, but it's not on your final. Cindy says, what if you didn't do the race? Like you were working on sequences in the series, but you didn't get to race? I would think that the problem would still be pretty doable. The race is just about a sequence. I think it'll be fine. We're going to check your honors requirements on finals day. I'm certainly going to check your honors requirements before I turn in grades by Monday. I don't know if that'll be on finals day. Cool. Those are all reasonable questions. I will see you all later. Good night. Have a good evening, and good luck in the next couple of days with both my final and your other finals.